In this presentation, we look at gait signals and what a gait signal reveals about a person. So I'll first introduce to you what gait is and the pipeline, and we look at the motivation behind the research and the research questions. Then we look at the methodology, results, and the future work. So gait is how a person walks. So when you're walking, you will move about your hands and legs and your entire body in a certain pattern. And this pattern will repeat from step to step. And this pattern is unique from person to person. Therefore, this walking pattern can be used as a behavioral biometric to identify a person. So that is called the gait pattern. So gait can be broadly divided into two sections based on how it is captured. First one is using external sensors, and the most common method to capture externally is using video input. In that scenario, we will get a video input like this. Then after detecting the human and the gait cycle, you can extract a gait energy image like this. This gait energy image can then be used to extract features, and you can do classification or other predictions on top of those features. Other than the external features, external sensors, you can also capture gait using on-body sensors. So for example, on any mobile phone these days will have an accelerometer and a gyroscope sensor. When this mobile phone is in your person, say in your front pocket or in your hand, when you're moving, when you're walking, the sensor data can be used to capture the walk movement pattern. So the input in that scenario will be a signal like this, and you can also use this signal to extract features either using the gait cycles or window data and do your predictions on those features. So the motivation behind this is by looking at different gait patterns, we know we can identify a person. So for an example, if you see someone very far away where you cannot see their face, but sometimes you can recognize them by the way they walk. Let me give you some more examples. In these three images, A, B, and C, I have given you gait energy images of three different people. Just by looking at this pattern, can you identify who is 8 years old, who is 26 years old, and who is 75 years old? By looking at this, I think you can guess that person B is the youngest and person C is the oldest, right? Similarly, now looking at these two images, can you say who is male and female? Yes, I think you can. So here, just by looking at the gait energy image, you could predict the age and the gender of the person. So in these gait energy images, you have a silhouette of the person. You see, looking at that, you can see their posture as well as how they walk. So now the question is, if we have only on-body sensor data, can that be used to reveal these details as well, such as age and gender? So keeping this motivation in mind, so these are our research questions. First one is, does on-body sensor gait reveal this personal information? So first, we will look at physical traits such as age and gender, which we discussed just now, and also things like height and weight. So for an example, if a person is very tall, their stride length will be longer. If a person is shorter, their stride length is shorter, right? So you can see there's a direct correlation between height and how they walk, which in turn tells us we should be able to find a relationship between the gait pattern and their height. So that's the thinking behind this. Also, we would like to go beyond physical traits and see if we can guess socio-economic traits like income level, education level based on gait patterns as well. So the next question we would like to answer is, the on-body gait data can be collected in many ways. Many different sensor locations like the wrist, if you have a smartwatch, or your front pocket or back pocket, or while you are holding your phone like this, So there are various different sensor locations. And throughout a day, you will be doing various actions. You might be walking on a level ground, you might be running, you might be going up or down a staircase, and so on. So out of these different sensor location and action configurations, which of these are most revealing and which of these are not revealing? So we'd like to find that out. Finally, we would like to see if there is a sensor configuration which will provide the Gait utility, which can be authentication for our mobile phones. We want to be able to provide this Gait utility while preserving the privacy. So for an example, we need to be able to use the Gait signal for authentication, but hide the details about gender and age. So is this possible? So these are the research questions we try to answer here. So to do this, first we need a Gait dataset for on-body Gait data. So looking at the existing data sets, we find three major limitations. First two are the limited amount of sensor locations and actions in the datasets. And also most of the sensor locations are not day-to-day mobile phone or wearable sensor locations. And the third one is most of these datasets do not have additional information about people, such as age, gender, height, weight, and so on. And we need these additional attributes if we are going to predict them using the on-body Gait data. So to overcome these Gait data existing issues, we decided to collect a new data set which overcomes these limitations. So to do the data collection, we first get participants to come to the NUS track and fill out a personal data form. So in this form, we will collect all the age and socioeconomic data I mentioned. Next, we measure the height and weight on site, and we proceed to put on these sensors. So the sensor unit is Axivity AX3 sensor, and we have three of those sensors. So we will be collecting data streams from three sensors at the same time. The sensors are worn on the body using these elastics and fabrics so that the sensor orientation does not change from participant to participant. Next, the user will do different actions in a laid out path on the track. So they will walk on a flat surface, run on the flat surface, go down an incline, up a staircase, and so on. So after all the actions are done, we change the sensor locations and redo the entire process. So after the data collection, we have 53 identities with 6 different sensor locations, if you can see. Blue color on the left and red color on the right, and the green color one includes different mobile phone locations, like on a call, in your side bag and back pocket. And we have 6 actions as shown here, and we are collecting the data in this terrain in this manner without any stops. We will capture the timestamps from timestamps where we switch between actions and later chop the data in pre-processing. Along with this Gait data, we also collect another data set to see the opinions about privacy. So for an example, we'll be collecting a lot of additional informations, physical and socioeconomic information. So we want to see out of this information which are more private to a person. For their perception, what do they feel like they value most? Is it age? Is it height? We'll be using this to later come up with a singular privacy index value, which we will use to determine which sensor locations are better suited for privacy preservation. So this data collection is an online survey done through SurveyMonkey. And let's look at the results, data collected here. So these are the two collection summaries. In the Gait dataset, we have 53 participants, about 26 females and 27 males. And the opinion survey, we have 566 participants giving their opinions about different values for the attributes. So this is a sample of the collected data. You can see the X, Y, Z axis values for the accelerometers worn in different sensor locations. All of these are for the same person while they were walking on a flat surface. So for the prediction of different attributes, we'll be extracting features in two different methods. First one is using statistical features. The second one is using RNN-based features. So for both of these, we'll be using a window size of 30 data frames, and we'll be using a rolling window-based method. After extracting the features, we'll train different classifiers and regressors for each of the different prediction tasks. So these two tables summarizes the results for the personal characteristic predictions. In the top table, you will see how we were able to predict gender, height, weight, age, and BMI while changing the sensor location. For all of these tests, the action was kept as a level walk. So you can see we can actually achieve 100% accuracy for gender. So keep in mind we are doing a 80-20 split, which means we'll have about 40 subjects for training and about 10 subjects for testing. The bottom table is a similar thing where we fix the sensor location and change the actions. So to get a better understanding of how well we are doing with the prediction of age, height, weight, and BMI, because the RMSE values, we look at this summary table. Here we have both physical and socioeconomical characteristics here. In the first set, we see a baseline result here, which is just the accuracy we can get by predicting the most common label or predicting the mean value of the test trained data set. And you can see the best performing model from our training in the next column, and you will see the percentage improvement finally. So you can see we can actually achieve a big percentage improvement over the baseline for all the physical characteristics: gender, height, weight, age, BMI, and also activeness. But we were not able to achieve a significant improvement over the baseline for socioeconomical characteristics such as extrovert, introvert, income level, occupation level, and so on. So this table gives a comparison between the different biometrics used for predicting the same features. So you can see that lots of research has been done for predicting gender using different biometrics: face, iris, fingerprint, and so on, right? So most of those different biometrics are able to achieve more than 90% accuracy for predicting gender. And now if you look at age, height, weight, and BMI, age prediction is similar between face and on body, but looks like age prediction has performed much better with visual gait. Height and weight, on-body gait has outperformed face-based height and weight predictions. So next, we want to see, to answer our final research question, we want to see which sensor configuration can be used to provide gait-based utility, but preserve the privacy issues as well. So in other words, we want to be able to use Gait as an authentication method, authentication biometric, but we also want to make sure Gait doesn't reveal other information like height and weight. In order to do that, first we need to understand which of the characteristics is perceived to be more important to a person. So this result down here is from the survey we did to get that understanding. So you can see the relative importance index from the results of that survey shows us people find that weight is the most private attribute out of these 6. BMI is the next most important to them. And it goes on like that. And finally, gender is the least private information according to the survey participant. So we are going to use these values to come up with a privacy vulnerability index. This privacy vulnerability index will give us a way to consolidate all the different attributes and their predictiveness together to come up with singular value, so we can easily compare between different sensor configurations. So we'll calculate a PVI as a weighted sum like this. The PI is how well we can predict an attribute. Either classification accuracy or the relative RMSE values will be used here. And SI will represent how important each attribute is. So the relative importance index values shown earlier, something similar to that is calculated using pairwise comparison matrix, similar to an analytical hierarchical process approach to calculate the SI values. So putting together the SI and PI values we have already calculated, we can come up with the PVI value for each sensor configuration. And similarly, we can come up with, using each sensor configuration, we just train a classifier to do authentication. So now we have the classification accuracy to measure the utility and the PVI value to measure the privacy invasiveness. Putting these two together, we come up with this graph. So if you look here, the highest accuracy is provided by the front pocket and the back pocket. Out of those two, you can see the front pocket is more privacy invasive because the PVI value is higher. The back pocket has a relatively lower PVI value. So simply switching the phone from the front pocket to back pocket can increase the privacy aspect of Gait sequence. Phone call here is for holding your phone up to your face. That provides the lowest PVI value, still providing around 80% authentication accuracy. So in this presentation, we introduced a new Gait dataset and used this Gait dataset to predict different physical and socio-economical attributes. And we saw that we are able to predict different physical characteristics with a higher improvement over baseline. We also saw how different sensor configurations and different actions give different results for these same predictions. And finally, we looked at how changing the sensor configurations affects utility versus this privacy invasiveness using a privacy vulnerability index. Finally, as future works, we would look at gate-based authentication in depth by changing sensor locations and actions and seeing how gate-based authentication can be extended into sensor and action independent continuous authentication scenarios. Thank you.